Hey there, and welcome to your next lesson on high level mathematics. So, we're making a start on probability today. So, we've dealt with things when we're trying to calculate an exact value of something, or sometimes with estimation before, we're estimating a true value of something, but there is a true value, like a right value and a wrong value. But here now we're dealing with probability, where it's more like what is the chance of something happening? So it could go one way, it could be the other, and so it's like this fuzzy sort of grey area in between. That's what probability is. So we're going to be looking at how do we deal with that. And today we're looking at likelihood and expectation. So how do we uh, measure or quantify the likelihood of something? And what do we expect? And how can we use that to then calculate what we expect to occur in a particular event? So here we go. So we're going to look at, first of all, different types of probability. We've got qualitative probability and quantitative probability, which is very similar to the concepts of, like qualitative and quantitative data, like we saw in statistics. So, whether or not it's numerical or not. We're going to look at relative frequency, which is when we can calculate, we can use the frequency of events to then estimate what is the probability of something, because sometimes the probability of something is not always just, obvious. We might have to actually, through experimentation, estimate what it is. And that's what we'll do there. And then finally, expected value. So what does that mean? What does it mean, the value that we expect to occur, and how do we calculate it? So we'll look at qualitative probability first. So qualitative probability is a way of describing a likelihood without using precise numerical values. So we're going to use words like likely, unlikely, certain, impossible. So it's more like just a rough, what is the rough chance of something happening? And so, we could think of it along a spectrum or an axis like this. On one extreme, we have impossible, absolutely no chance of it happening, and then certain at the other end, which is 100% chance it's going to happen. Dead in the middle, we've got 50-50. Could go either way, like a toss of a coin, heads or tails, 50-50. And then halfway in between, you could see is likely or unlikely. So it's like unlikely is then starting to go close to impossible. Not close to it, but like, on in that bottom half, and then likely will be in the top half. And we could be even more precise if you wanted to say very likely, or something that is almost certain. Something that might be like not 100%, but very, very likely. And same thing in the opposite direction, like, or almost impossible, because we have plenty of events like that as well that are, it's not impossible, it's just very, very unlikely. So that's how, those are the kind of words we would use to describe something. And there's various advantages why we do that. Because you might think, okay, if we can, calculate probabilities exactly, like with numbers, why would we bother just using these descriptive words? And there's various reasons why you might do that. Like you as a scientist or mathematician, you might be calculating something, like say in your job, and then you have to present that to, a board of people who maybe aren't mathematically minded like you are, and so you would then use these more descriptive words to for them who then maybe are conducting the business side of things to then make decisions. They don't need a precise number. They just need, is it likely? Is it very likely? Is it impossible? Whatever. Or it could be something like dealing with sensitive situations, like say a doctor who needs to tell someone, oh, there's only like a 5% chance they're going to survive, some operation. That would be very insensitive, usually to uh, use numerical values like that. Instead, you would just say, oh, it's unlikely, or, we need to manage your expectations, or, use these more descriptive words to be sensitive. So those are some examples of when you might use qualitative probability. So the typical kind of problem you'd be given on qualitative probability is something like this, where you're given a spectrum between 0 and 1, which is basically proportion as a decimal, or a fraction, 0 being impossible, 1 being absolutely certain. And we could put certain things happening on that spectrum, say like the sun rising in the west, pretty much impossible, barring some crazy astronomical event. Um, or at the other end, certain would be the sum of two odd numbers being even. That's a mathematical proof we can show that, yeah, the sum of any two odd numbers is always going to be even. So that would be a probability of 1. You could take something like this, like winning the lottery. We would put down this end, wouldn't we? It's very, very unlikely, but it's not impossible. Or you could put something like this: a randomly chosen tree shedding its leaves in autumn, because most trees do shed their leaves, don't they? So if you randomly chose one, you can see it's going to be quite high up the end. Not quite, as extreme as winning the lottery, but it's pretty high. You could take something like this, and we would put here, say, getting a seat on a train at Russia. You could imagine putting there, where it's unlikely, but it's not like really, really unlikely. It's just, but quite unlikely. So we'd put it down that end. Something like this, it raining sometime in the next month. Certainly in the UK, where we get a lot of rain, it raining at some point is going to be pretty likely. So we'd put it up, say that end. You could have some other examples like this. Roll a number less than 3 on a fair dice is only like a third chance. Or this, there being at least one goal in a football match. Might be quite likely, like just slightly above 50-50. So you'd put it there. Or something like this, like correctly guessing the gender of a newborn baby would be 50-50 because you just got one of two options. So there's some examples of things that you'd be given, and you just kind of need to rationally kind of deduce where that would go on there. I've given some what I think are more interesting examples here, but typically some of the examples you get, it's normally quite obvious where they would go. So quantitative probability. So we've looked at how we would just kind of roughly, qualitatively, assess what is the general likelihood of something. Now let's look at how we'd actually calculate it. So we need to get more specific now. So we have a few keywords we need to know. First of all, sample space, which is what's like when you have something happening, the sample space is this set of all possible outcomes that can occur. For any particular outcome or set of outcomes from the sample space is what's referred to as an event, and that's what we're normally trying to calculate is the probability of an event occurring. So some subset of all possible outcomes that can occur. We calculate the probability of an event by dividing the number of outcomes that correspond to that event by the total number of outcomes in the sample space. But one thing is that this only applies for when the sample space is unbiased, which means that all the outcomes are equally likely. We'll take a little look at bias soon enough. So let's take the example of rolling a single unbiased die. So it's a fair die. Every side is equally likely to land on. So the sample space would be simply the numbers 1 to 6. Those are your all your possible outcomes, isn't it? 1, 2, 3, 4, 5, 6. You can't roll a 7, you can't roll a 0 or anything like that. So that's your sample space, 6 possible outcomes. And let's say if we're considering a couple of different events here. So event A being the die landing on a 6, and event B being the die landing on an even number. And we can now calculate the probability of those events. So we would normally use this notation here where we do P in brackets A. So it's kind of a similar notation to a function, but you've always got to be aware of the context of a question. So in probability, P of some number, some letter, say here, or it could be even text. It's basically saying the probability of that thing. It's not a function. So yeah, be aware of that. Sometimes we have the same notation meaning different things depending on the context you're working in, whether it's algebra, say geometry, or in this case, probability. So the probability of A, we have this funny P symbol, which you can just use a regular P, but in mathematics, this is like formally the notation we use. And it's 1 in 6 because it's one possible outcome out of a total of 6 outcomes. So, landing on a 6 is just one possible outcome out of the total of 6 possible outcomes. So we get a 1 in 6 chance, whereas you see the probability of event B is 3 in 6 because there's 3 possible outcomes that correspond to that event, like the event being the die landing on an even number. So that's a 2, a 4, or a 6. So 3 possible outcomes out of a total of 6, we get a half. We're going to, just simplify that fraction. So it's 50-50 chance of getting that. So this is the very foundation of what a probability is. You're basically just taking all the possible outcomes that can occur. You then find the number of those outcomes that correspond to the event you're considering, and then you divide that number by the total number of outcomes, and that gets you your probability. So whatever as we move on to more complicated scenarios, that is what the probability always is. It's just that that fraction essentially. So hopefully, yeah, that simple example explains that. Let's look at bias quick. So the term bias has a similar but different meaning in the context of probability. So we've seen this in statistics, which is when it basically kind of leans the data in a particular direction, maybe not even the correct direction. In probability, bias is not necessarily a bad thing. It's more just something you need to be aware of. So when a scenario is biased, it means the probability of possible outcomes in the sample space aren't all equal. So if we're trying to calculate the probability of an event in a biased sample space, we need to be aware of the different probabilities of each of the outcomes. So suppose I have a loaded die. So the die is biased to land on 1 and 6 more often, twice as often, in fact. We would then get these following probabilities for each outcome. These are our 6 outcomes, aren't they? But they're not equal this time. Like last time, they were all just a 1 in 6 chance. So 1 in 6 each. And so if we had, say, like the probability of landing on an even number, which occurred, corresponded to 3 possible outcomes, it was then 3 in 6. But in this case, we would have to, be mindful of these different probabilities. Which, by the way, you could work this out using algebra. Like, say, if you let the probabilities of 2 to 5 be x, and you let the probability of then 1 on 6 being 2x, because it's twice as likely. If you add all that up, you get 8x, which is equal to 1, because it's 100% chance of getting one of those options. And so you then get x equals an eighth. So 2x is 1/4. You see, using a little bit of algebra, you could work out what those fractions would be. So once we've got this, if we now wanted to calculate the probability of landing on 1 would be 1/4, whereas the probability of landing on a 3 would be an eighth, even though they only correspond to one event in the one outcome, sorry, in the sample space. You see the probabilities are different. And if we wanted to do, say, the probability of landing on an even number, it's going to be an eighth plus an eighth plus 1/4. Which in this case you find still comes out to a half, but you see the calculation's different. If I instead wanted to do the probability of it landing on, say, a 1, a 3, or a 6, even though it still, again, corresponds to 3 outcomes, it's going to be 1/4 plus an eighth plus another 1/4 is going to be, what would that be, 5/8. So not quite a half, it's actually a little bit more like. So you see, it changes things. So that's how we deal with bias. Now let's look at how we deal with multiple events. So we just looked at simply um, like a single thing that is happening, like a roll of the die. It just happens once, and we're looking at one particular event that could occur. And now we're looking at what is the probability of, say, this event and then this event happening, or this event or this event happening. And or are two sort of keywords you need to be aware of here. So we're dealing with multiple events. We can essentially calculate the probability of them together by essentially calculating the probability of them individually and then doing some arithmetic with that. So if we want to calculate the probability of event A or event B, so we've got 2 different events here, we simply add their individual probabilities. If we want to calculate the probability of event A and then and B occurring, we simply multiply their probabilities. So our list only applies to independent events. So we're going to look at dependent events in a later lesson. So independent events, very briefly, is basically when the probabilities of something doesn't change from one event to the next. So say if I'm tossing a coin and it's 50-50, if I toss it once, the odds, on the second toss is still just 50-50. It hasn't changed. So that's what an independent event is. Dependent is when probabilities change from one to the next. So we're not worrying about that for now, though. So let's take a simple example. Like, say if I've got a spinner with 3 colors on it, and the probability of each corresponding, to the size of that area, essentially, on the spinner, we get different probabilities. Now, this is a typical kind of thing you might get asked, and you've got these 3 possible outcomes, but you see one of them is missing, and we need to find out what that is first before we can move on. So we want to find out what the probability of green is. So I've done probability of G being just the event of it landing on green. We can calculate that doing this calculation here, because we know all the probabilities together must add up to 1. That's always going to be the case, because this is our sample space: blue, red, green. These are our 3 outcomes we can get, and it must land on one of them. you know, if you spin it, it's going to land on one of them. And so it's 100% chance it will land on one of them. So therefore, all three of them added together must add up to one. So we can find out what the green is by doing one, subtract the other two. And we just have to do a bit of proportions, bit of fraction manipulation here to, be able to do that calculation. So there is a lot of this, a lot of work with proportions, not just fractions, but also decimals and percentages. So if you're not confident with those, I would highly recommend you go back to our lesson on proportions, lesson 2 of numbers, and you'll make sure you brush up on that because you'll need that for your probability. So if we now want to do the probability of red or green, so that's basically you're spinning the spinner, and we want the probability of it then landing on red or green. So that gives us two possible options there, and the probability of each is then just we can add them together if we want one or the other. So that would be 2/3 plus 1/12. And again, use our knowledge of fractions, we can add that together and then simplify, and we find it comes out to 3/4 or 75% chance. Similarly, if we want the probability of blue and then red, it's going to be 1/4 times 2/3. And so we can then do that multiplication quite simply, can't we? And simplify again, and we get a 1 in 6 chance. So that's going to essentially be when we spin the spinner once, and then we're going to spin it again. Because obviously, when you spin it once, it can't land on both blue and red. That doesn't make sense. It can only land on one or the other. So you got to think about kind of what's actually going on here. We're spinning it twice, and we spin it once. Yeah, so we spin it once and twice, and then we're seeing what is the odds of then getting a blue and then a red. Or maybe not. Maybe we could do we just want a blue and red, and we don't matter what order it's in, and that's what we need to look at now, which is combinations. Because this here, what we've got here, we need to be very specific about what we're talking about here. So there, we need to consider order. So is there an order of things? So because with this, because like I was saying, there's two spins going on here when we're doing blue and then red, but equally we could have had red and then blue. And if we're not worried about the order, we just want like a blue and a red in either way. We need to take into account those combinations. So in this case, yeah, like I said, blue and red, that's what we've actually calculated. There's the probability of blue and then red. And because these are independent events, we'll have the probability of red and then blue will be the same. It'll come out the same because the probabilities don't change, do they? So we've got this probability times this probability. Well, if we do it the other way around, with the multiplication still going to be the same because we know when we multiply things, it doesn't matter what order they're in. So for independent events, it's just going to be the same. And then, so the probability of then a red and a blue in any order is we add their probabilities together, we're going to get this, which simplifies to a third. So this the concept of combinations. What we're doing, to a particular event, there's actually many possible combinations that correspond to that event, and we need to take into account those. We have a combinations function for more complicated combinations that can occur. Like here, it's quite simple because it can go blue red or it can go red blue. But sometimes you get more complicated ones, and we have this formula for it, which is quite a complicated. It might appear like quite a complicated formula. So it's like this function c, and it takes input n and r. So that's function notation there, taking in input of n and r, which sometimes we represent like n r in a vertical column, kind of like a vector, but it's not, again, in the context of probability, it's not a vector, it's this combinations function, which has this form of n factorial over r factorial times by n minus r factorial. So if you haven't seen a factorial before, we're going to look at what that is. How we actually put this in our calculator, you need to be able to spot where it is. So typically we need to press shift first, and then we press this button down here, so NCR. So say if I wanted to do this combination with the inputs of 3 and 2, I would do 3, C, and 2, and it then calculate that is 3 combinations. So let's take a look more detail what that actually means. So if I put in that value of 3 and 2, we calculate this. And first of all, factorial is basically the product of all numbers up to that number. So 3 factorial is basically 1 times 2 times 3. And then 2 factorial is going to be 1 times 2. We have 3 minus 1 in there, which is, 1. And, 1 factorial is just 1. So it doesn't really, similarly, 0 factorial is always 1 as well, if you ever encountered that. So that's how we calculate a factorial. So you see here, we've got a fraction. We can just simplify that and we get 3. So, okay, what this is saying, so when we have, how we would often pronounce this, combinations, we would say 3 choose 2. And what that means is, out of a total of 3 possible, 3 things that can happen, we're asking how many ways can we have 2 things in those 3 things. So it'd probably be better to explain with an example. Like say if I toss a coin 3 times and I'm looking for the probability of getting heads twice, I can work that out, of say 2 heads and a tails. We know that's going to be a half times a half times a half. But then we need to consider how many combinations that is. Well, we can get heads, heads, tails. We could get heads, tails, heads. Or we could have tails, heads, heads. If you try that for yourself, you'll see there's those are the only 3 combinations we get. And so that's why we get the value of 3 here. It's telling us how many ways from, 3 tosses of the coin can we get 2 heads? Like where can those 2 heads fit? So the combinations calculator, it works when we're looking at something where we can have something happen or something else happen. Only like those 2 options. Or you might have the probability of, one thing happening and then not happening. So similarly, we could have, say, the roll of a die 3 times, and we're looking at how many 6s we can get, and we're looking, okay, how many ways can we get 2 6s out of 3 rolls? Well, you could get 6, not a 6, not a 6. No, sorry, you could get 6 6, not a 6, or you could get 6, not a 6 6, or you could get not a 6 6 6. So it kind of works in very much the same way. So let's look at a more complicated scenario. So say if you had like a toss of a fair coin, like an unbiased coin 10 times, and we want to know the probability of getting 7 heads. How we would do that is, okay, we could look at just a specific order this first. So the probability of 7 heads and then 3 tails. So it's a half for each of those 7 heads and a half for each of those 3 tails. So we get a half to the power 7 times half to the power 3. So it's basically half to the power 10, which we can work out to be 1 over 1,024. So that's a probability of one specific outcome, but we know there's many different combinations of that could occur there. So we want to know how many different ways can we put 3 heads, how many different ways can we put 7 heads in 10 tosses of the coin. So you could get 7 heads and then 3 tails, or you could get 3 tails and then 7 heads, or you could get 2 heads and then 3 tails and then another 5 heads, and so on and so forth. Like there's so many different combinations that can occur here. How could we calculate what all those are? That's where the combinations formula comes into play. So we want, out of a total of 10, how many different ways can we put 7 heads in that, those 10 options? That's what that's basically calculating. And if we simplify that, so we've got 10 factorial, so that's 10 times 9 times 8 times 7 times 6, all the way down to 1. 7 factorial is 7 times 6 times 5 times 4, all the way down to 1. So you can see straight away, 1 to 7 on the bottom is going to cancel out with 1 to 7 on the top. So we're just left with 10 times 9 times 8 on the top. And on the bottom, we've just got the 3 factorial, 3 times 2 times 1. So you need to be able to spot how to cancel those common factors. We've seen how to do that, with simplifying fractions before. We need to do that here. If you have to use this formula, if you don't have a calculator available to you, but often you will, so it's fine. As long as you know how to put it into the calculator, you'll be okay. Then we can always just, simplify this fraction a bit. Like I'm cancelling out the common factors of 3 and 2. And you see it comes out to 120. So there's actually quite a lot of combinations. You might not think it would be so many, but there's a lot of combinations we could do there. So the actual probability of getting 7 heads and 3 tails in any order, again, because the probability of all of them is 1 over 1,024, because these are independent events. So it doesn't matter what order we do them in, the probability is always going to come out the same. So we just take that probability and times it by 120, because we need that basically added to itself 120 times. So we'll get this, and we can simplify to this. using our understanding of proportions, we could put that as a decimal, we could put it as a percentage. So you find the probability of this happening is 11.7%. So this is an example of then using combinations. So when we've got the probability of one event and then another event and then another event, we're doing this and this and this and this. We times them all together like we did there, like a half times a half times a half, and we got 1 over 1,024. But then we also have to then times that by the number of possible combinations that could occur. Otherwise, we're looking at a very specific ordered event sequence of events as opposed to any combination of events. So that's our combinations. And so, see, something like this is a common kind of thing you might get asked. And this should be quite clear now what the answer would be. So if two people toss a coin 3 times and one person gets 3 heads and the other gets 2 heads and a tails, are these both equally likely? So you might, like one person might think, yeah, they'd be equally likely because, it's 50-50 whether or not you get heads or tails each time. So if you toss it 3 times, it's just going to be 1 in 8 both times, regardless of what you get. And that is true if you're doing, if it's ordered. If I was talking about specifically getting 2 heads and then a tail, but we're not. We're talking about just getting 2 heads and 2 heads and a tail in any order. And so if we calculate that now, we can see actually the probability of getting 2 heads in the tail is 3 times as likely because there's 3 combinations of doing that. Whereas with 3 heads, there's only one combination: heads, heads, heads. There's no other combination you can do. So you see, actually, no, the probabilities are different. So that's combinations. So that's it in terms of calculating the probability of independent events. So we need to, we've got uh, what it actually means to be the probability of an event, how to then deal with when we've got multiple events, this event or this event, or you have this event and this event. And then when we're dealing with this event and this event and then this event, we know how to deal with the combinations, which will affect the probability of it happening. Now let's look at relative frequency. This is when we have, say, something like this, like a biased coin, but we don't know how it's biased, and we want to measure it. Therefore, so we don't know what are the probability of getting heads and tails. We want to estimate these probabilities through experimentation. How can we do that? So we got these 3 people, and they're all going to test it each, and they toss the coin a whole bunch of times, and they record how many heads and tails they get, and we can then use this to calculate what, like an estimate for the probability of heads and tails. So for Adam, that his estimate for heads is going to be 6 out of 21. Because you see there, he's tossed the coin 21 times, 6 heads and 15 tails. He's tossed it 21 times, he got 6 heads, and then he got 15 tails. So this would be like an estimate of how many heads and tails I got. Because say if it was a fair coin and I tossed it 100 times, you would expect it to come out 50 heads and 50 tails because 50 over 100 is a half and 50 over 100 is a half again for the tails. This is something what's known as expected value, which we're going to move on to soon enough. But you can see how, you would expect the probabilities to match, this proportions, the relative frequencies between the heads and the tails. So we can calculate the same for Jack. We can calculate the same for Amy. So they've each got their own estimates for the probability of heads and tails. And so you see, they're not always going to be the same because each one is going to estimate slightly differently based on, random chance and what happened when they tossed the coin. We can simplify those fractions to this. And now, say if you was asked whose estimates for the probability are most likely closest to the true values. Now, this this is where you can kind of see the probability is closely, quite closely related to statistics. So what we've got here is like an experiment, and each toss of the coin is like our sampling, like we're producing data points here, and we want to analyze them this data. And we know that when you take a higher sample size, it tends to be more accurate because it's more data, it's more information, and it gets you more accurate results. And so, if we take a look at these proportions as decimals, you can see the probability of heads is somewhere between zero point 0.2 and zero point 0.3. The probability of tails is somewhere between 0.7 and 0.8. Amy's ones will actually be the most accurate because you see she did the most tosses of the coin. She tossed it, what, 68 times, whereas the other two only tossed it like 20 something times. So that will, her answers will be closer to the true answers. And we'll see why that is in a second when we look at expected value. But let's see, okay, how could we actually get a more accurate result for heads and tails? So, okay, using that idea, the more tosses of the coin, the more data points we produce, the closer we're going to get to the true value. Okay, we could make this more accurate by getting them to, maybe toss the coin more times. Or perhaps what we could do is just simply combine their data. So you see here, we could just total up how many heads and tails they all got together. And then the probability of heads is then going to be 27 out of the total number of tosses. Again, going back to the very definition of what a probability is. So the total number of tosses is 27 plus 87, so that's 114. So it's 27 out of 114 is our estimate for heads. The probability of tails is, our estimate is 87 over 114. And if we put it as decimals, it's going to be this and this. So that would be an even more accurate result, or at least more likely to be accurate. There's no guarantees. Like say even with a fair coin, I could toss it 100 times and maybe get heads every time. That can happen, but it's really, really unlikely. So that's what we're going to look at now is more expected value. So we've seen there that when we combine data, we get more data points. We get more accurate results. And this is something that we do in real life. Like many scientists might do many different studies on a particular topic. And then once we've got many different studies, you might have someone come in and do what's known as a meta-analysis, where we then pull together all the data from all these different studies, and it will get you an even more, because the more data you get, the more accurate you get to the true value, what is known as the expected value. So let's look at that. Expected value is referred to as the expected frequency, or sometimes just simply expectation. So that's the key words you need to be familiar with. Expected value does not necessarily equal one of the possible outcomes, as we're taking an average, and we've seen this before. Like you could average a bunch of integer values and you'll get a decimal value, and that's okay. That can happen. It's expectation is akin to an average. So if we toss a fair coin 150 times, our expectation would be 75 heads, 75 tails, based on the relative, probabilities. There's 50% chance of each. So we expect that out of 150 tosses, 50% of them will be heads, 50% will be tails. That's not a guarantee. Like I said, we could toss this and maybe it comes up heads 150 times. That can happen, but it's really unlikely. What we expect to happen is half and half. Same thing if we roll a fair die 135 times, we'd expect to roll a 6 1/6 of the time, because the probability of rolling a 6 is 1/6. And so we do 1/6 of 135 and it comes up 22.5. So that's on average, we'd expect, 22.5 heads, sixes, sorry. Which is, like I was saying, that's a decimal number, but it's okay because it's an average. It's just on average. So if we roll two fair die together, what is the expected outcome? So this is a bit more of a tricky example. Let me show you how to work something like that. So first of all, we need to kind of add up all the possible outcomes, and so that's might be a bit cumbersome, but there's some ways we can speed this up. So first of all, say we could assume, say if we roll a 1 on the first die, and then what do we roll on the second die? We could get, say a 1, 2, 3, 4, 5, 6. And so this would be all the possible outcomes. So you'd get 1 plus 1, or 1 plus 2, 1 plus 3, 1 plus 4. If we put that together, we're essentially getting this little sequence, which adds to 27. Now, if we do the same thing, okay, assuming we get a 2 on the first die, okay, and then we could get either 1, 2, 3, 4, 5, 6 on the other die. This would then be all the possible outcomes. And we put those together, and you see we'll get 33. And you can start to see a sequence occur in here. We're getting 2, the addition of 2 to 7, and then 3 to 8, and then 4 to 9. We can kind of see what that sum is going to be. And we have to repeat this, 3 more times for the first die being either a 4, 5, or 6. And those additions, 27, 33, 39, you can start to see the sequence that's going on there, that they're increasing by 6. So we're using our knowledge that we did um, before at the end of algebra on sequences. You can see this is just going up by 6 each time. So we can see this for our 6 possible options for the first die. You know, the sum total is going to be these 6 numbers, and we can then add those up. So this is all the possible outcomes of rolling 2 die together, added together, and we now have the expected value is then going to be that total divided by the number of possible outcomes that can occur. So we know there's 6 possible options for the first die, 1 to 6, and then for each one of those numbers, 1 to 6, we've then got 6 possible options for the next die. We can look at this more when we start looking at frequency diagrams, frequency trees. We'll be able to see that more explicitly. But we see because there's 6 options for the first and 6 options for the second. In total, there's going to be 6 times 6 options, which is 36. And so, okay, we do the total sum divided by the total number of options. It's essentially an average, gets us 7. So on average, we would expect to get a 7. So that would be the expected outcome. It's what's most likely to occur. And if we was to roll those 2 dice over and over and over and over again, and we average them all together, we would expect to get, you know, it to average to 7 over time. So um so yeah, I just wanted to show you a quick example here of why this expected value, why we converge to that expected value as we take more and more data points, because that might not always be clear. So say if we take something here like the toss of a fair coin, and we're going to look at what is the probability of getting 40 to 60% heads, 60 to 80% heads, or 80 to 100% heads for 10 tosses, 100 tosses, or 1,000 tosses. So you see there, we've got the first case where it's 40 to 60% heads, which is what we would expect, you know, somewhere around 50-50. Then you're looking at 60 to 80%, and then 80 to 100%. We're looking at progressively more extreme results, you know, far away from what we'd expect to occur. Um, and you wouldn't be expected to calculate these probabilities. This is a bit beyond GCSE. I'm just sort of showing this here for like, you know, illustration purposes. So you see here, you see how as you go further and further away from what we expect to occur, like the probability is going down. So that's why so you see we say this is the expected value because it's kind of like what's most likely to happen. But what the interesting thing is that happens is like as we increase the number of data points, so increasing the number of tosses, you see this uh, it becomes even more precise. Like you see the odds of it being around like that expected value starts to become even more likely, like 96.5% chance that it's going to be, you know, give or take 10% around the midpoint. And the probability of getting say 80 to 100% is virtually zero at this point. Like I just said, approximately equal to zero. And if we go one step further and we do 1,000 tosses of the coin, we find that the probability of getting somewhere between 40 and 60% heads is almost certain at that point. And the probability of getting, you know, even just 60 to 80% heads is like virtually zero. So this is the important, like if you actually calculate the probabilities on these things, you see as you increase the number of tosses, the odds of it, you know, converging to that expected value of what we expect to occur becomes more and more likely. And so that's why you know, if you take enough data, it will always get to the expected value. And so here's like an example of like a graph of this. Like this is what's known as the law of large numbers. So again, you don't need to know this for your GCSE. It's just more to help you understand what expected value is. You see at the start there for the number of tosses on the x-axis, when the number of tosses is quite low, you see the percentage of heads kind of jumps around a bit because the odds of getting a value far away from the expected value is not so unlikely. That can happen. But you see, as the number of tosses goes up and up and up, it converges towards that 50% point, which is what you would expect to occur. And so this is the important, like why I say in stats, we need large sample sizes because it gives us the most accurate picture of what's actually going on in the real world. Because as you get more and more data, it's going to converge to like the true value, the expected value, what is like actually going on in the real world. So that's and same thing like when we saw when calculating the probability using relative frequency, we want more and more data. The more data we get, the more accurate the probability is going to be. So you can see here, you know, with a graph, why that occurs. Right. So here we go. That's it for today on our start introduction to probability. I thought I'd just give you a couple of interesting real life examples where probability plays a key role. So uh, jobs in finance and like where there's a lot of risk management going on, where you need to predict kind of the potential gains and losses that you might make within an investment requires a lot of probability to see what is like the expected value. If I make an investment, what do we expect to get from this? Do we expect to gain or do we expect to lose? And so that can then determine decisions you make. Another interesting field is something known as quantum computing. If you've read anything about quantum mechanics before, there's probabilities inherent to that, and so quantum computing a really important field going into the future. If you're interested in that sort of thing. Another thing is like autonomous vehicles. Soon we might have vehicles that drive themselves, and they have to deal with probabilities. Say if someone's crossing the street and you can't predict what that person's going to do, and so you have to deal with probabilities on that for the car to then make a decision on where it's going to drive. So these are all great areas. If you're interested in going to like a more mathematical, technical fields for your career, these are all great fields to go into if you're interested in, say, probability, if that's a field of math that you like. So here are our takeaways for today's lesson. So we're going to continue with probability next time. We're going to be looking at frequency and probability trees, which is a great way of sort of mapping out sequences of events and calculating the probabilities of those different sequences, and um, particularly dealing with dependent events. So this is when the probabilities might change from one event to the next. We're going to see how we deal with that. So I'll see you next time for more probability.